Another thing that should be considered are the Doppler shifts when there is the relative movement between the transmitter and receiver, but for our analysis we shall keep it to just the normal analysis. So the rake design techniques. So there are several ways to design rake, as I had mentioned, the all rake, selective rake, and the partial rake. Uh, uh, even in each of these, there are several ways to design a partial rake or a selective rake and so on. I'll be going through one of the three popular types of designing a rake receiver. So first thing is the MRC selective rake, which is the maximum ratio combining. So it is assumed that the channel estimation errors are white Gaussian noise. So if we go through this equation where h is the channel coefficient of a perfect channel and h dash is the channel coefficient after the where Gaussian noise is considered, NE is the variance of all the estimation errors of the Gaussian random variables. So the presence of channel estimation errors degrades the performance of the system, but this can be modified by equally weighting the performance, equally weighting the rake receiver fingers. So, but the performance improves only slightly. So weighting vectors should be weighted according to an MMSE estimation to give the best performance, minimum mean square error estimation. So using the 802.15.3a standard, we can observe that the envelope in an AWGN channel is a double exponential distribution, but in a high density environment, when there are lots of channels, lots of transmitters and receivers, it follows an exponential distribution. So assuming this, the weight of each finger can be calculated as follows, where weight of a finger k is given by 1 by 1 plus a into e power kt, where a is the ratio of estimation errors to the average power of only the first path. So calculating the ratio of estimation errors to average power of the first path is easier because we get the first signal that is encountered, and the weighting for the rest of the symbols can be can be calculated using this formula. So using this, it makes the path selection better statistically. Next thing is the group decision general selection combining rake receiver. So it uses group sorting and decision tree theory. So the multipath components are divided into several groups, and the best one from each group is selected. So if there are L resolvable paths or the L multipath components are present in a system, so these are divided into LC groups, and the best path from each group is selected. This is done by comparing the signal to noise ratio of each of these paths, and it is sorted into groups. So this formula gives the number of paths in each group. So the groups are assigned with increasing order of path delay, with the first one which starting from the least. So these chosen paths are updated after each coherence time. Hence the sorting happens after each coherence time. Since it is put into groups, the compare operations required are very few, and only a path with very high SNR is chosen. So if unequal SNRs are present for different paths, it gives rise to an exponential distribution, which can be used for further analysis. So adaptive rake. So like I mentioned, the first 60 delayed paths in the worst case capture 85% of total energy, but for the channel model 1, the 85% of total energy is present in the first 21 paths, but those many fingers are very difficult to implement. Hence we use an adaptive rake structure. So it requires only one pulse matched filter, and we can process the signal digitally. So the way a signal is given as follows, using this formula, where beta m is the weight and theta m is the finger delay of each of the paths. So pilot bits are transmitted at the beginning of a packet to estimate the amplitude and phase of the fingers. So a sliding algorithm processes only digital data. A sliding algorithm is used, which is used to process only digital data, so it makes the structure simpler rather than having any comparing algorithms and so on. So this algorithm cross correlates the received signal with a known sequence and it calculates the delays and gains. So to reduce the simple interference, an adaptive linear filter is used, and this filter uses the LMS algorithm, least mean square, and a sequence of training bits are also transmitted for the LMS equalizer to adapt to the channel. The Simulink model is as shown in the figure. Since it takes a lot of time, I have already opened the Simulink model. So it consists of an error vector structure, error control structure, and here you can see the transmitter consisting of a multipath channel here and symbol matched filter. This is known as the Rake receiver, and an error control calculation is also calculator is also in the Simulink model. So these are the initial parameters used for the Simulink model. The symbol duration is 0.1 millisecond. The processing gain is 16. Doppler frequency is 50 Hz. Number of fingers is 4. The processing delay due to Rake is 2, and path delay is mentioned. So it consists of a channel generator, wide Gaussian noise channel generator, which accepts the noise vector as input. So the transmitter uses the spread spectrum technology. The multipath channel has relay fading. The symbol matching filter is used to correlate the signal to a known sequence. A rake receiver is used, which uses the MRC selective rake, which had already been discussed. So 4 fingers are considered for this analysis. An error rate calculator is used to calculate the bit error rate and the packet error rate. So the results, the MATLAB code is here. So this is for a line of sight communication. So here we give the spread spectrum analysis, and the amplitude modulation used is the 16 quadrature amplitude modulation, 16-bit. So the symbols are generated in this part of the code, and spreading is done. Noise considered is the additive wide Gaussian noise. So a despreading and demodulation is done, and these considered the bit error probability and the packet error probability. By that time, I'll explain this part of the code. Yeah, this is for the Rake receiver, which uses the relay fading. So the Rake receiver has 4 fingers. So this is done. So these give the simulation, which will be discussed in a while. So it follows a similar code where symbol is generated, and the wide Gaussian noise is added along with the relay fading characteristics. The bit error rate calculation, and this is for generation of the spread spectrum signal and demodulation, and this is the calculation for the for the bit error rate and the packet error rate. These are for the first code, and these from the second code. It will probably take some time because the code is a bit large. We'll come to that in a while once it's done. So these are the results. So the first graph shows the bit error probability for 16 QAM in theory and when it is simulated. So you can see that it is more or less similar. It follows the theoretical calculation because there is no fading or interference or anything. So bit error rate falls to a very low value beyond 13 dB, which is as expected theoretically. So the analysis is very accurate with the theoretical value. The next one is the bit error rate curve for the 16 QAM, which includes the relay fading and the simulation, theoretical relay fading and the simulation. So the theory AWGN is what we had done in the previous graph, So this is for the present graph. So it, if you can if you can see the when relay fading channel is introduced, the uh, bit error rate drops drastically, does not drop drastically, and when AWGN um, is considered, then it reduces the probability that it can be transmitted accurately. So on simulation the values deteriorate further. So in theory, upon simulation the performance worsens considerably. So the line of sight communication is you considered here, again the first code. So the after the relay fading is considered, relay fading is put up again. So after a certain point at around 9 dB, so it's the performance deteriorates, and the performance it keeps reducing with increase in the EB by naught value. This is due to the multipath fading introduced. So to overcome this, we need to use a Rake receiver. So upon using a Rake receiver, the performance is as shown. So it highlights the advantages of using a Rake receiver. The EB by naught value, even when it increases, the packet error probability reduces slowly. So the superior performance is because the Rake receiver can collect all the multipath components and can give a better performance. So in conclusion, so we have discussed different techniques of designing a Rake receiver for ultra wideband communication. So how to generate a ultra wideband signal using spread spectrum, and the difference between a wide Gaussian noise channel and a relay fading channels are used, where the wide Gaussian noise channel can be used only for basic analysis. So MRC Rake receiver, selective Rake receiver, is constructed using Simulink, and its performance is analyzed. So in future work, different network performance parameters can be used to further strengthen the usage of Rake receiver. Maybe design other types of Rake receiver and compare the performance. And rarely do you see one single channel estimation have working in real life. So joint channel estimation can be done to analyze the performance. So in acknowledgement, I would like to thank Dr. Tepengu for the opportunity to do the project on this course. So I learned how to what a Rake receiver is and how it is advantageous to use a Rake receiver for a multipath model. So the complete autonomy to do the project helped me learn the different techniques and execute them. So these are the references that I've used. And thank you. And yeah, just so the code.